Now that we've introduced the basic ingredients of our model, it's time to study the behavior of firms and consumers. Now, when we think of the insurance firm, firms maximize expected profit. So we need to know what their expected revenue and expected costs will be. Here is how we will think about the firm behaving in this market. We will assume that the firm offers a contract C, a two-dimensional object CGCB, in exchange for the consumer's endowment E. So the firm gives away contract C and in return receives the consumer's endowment E. The consumer, if they accept the contract, will give away endowment E and receive contract C. Now, this may seem an unusual way of thinking about this. Typically, with insurance, you think a consumer pays the firm some amount. In both states of the world, they have to pay for their insurance. And then, if the bad state occurs, perhaps they receive some payment back from or a larger payment back from the insurance firm. Well, take my word that this is exactly the same as what we are assuming. The net effect of a consumer paying for insurance in both states and then receiving some money back in the bad state can simply be thought of as the firm offering a contract C and taking the consumer's endowment E. So we're going to think of contract C as the thing the firm gives away to the consumer in return for the consumer's endowment. So the cost of this contract C will be the firm's expected costs, and their revenue will be the expected value of what they receive from the consumer, which is their endowment. So the important point here is that the expected value of these contracts, the contract C and the endowment E, depend on the type of consumer that the firm is dealing with, because high-risk types have a higher chance of ending up in the bad state than low-risk types. So if we know the consumer's type, then we can calculate the expected value of a contract C, which is the firm's expected costs, as we'll denote this capital E subscript I for where I is the type, which is H, L, or X, high risk, low risk, or unknown type. Then, with some probability PI, the bad state occurs for this consumer, in which case the firm is paying an amount CB. And with probability 1 minus PI, the good state occurs for this consumer, in which case the firm is paying out an amount CG. So the expected cost of this contract is PI times CB plus 1 minus PI times CG, where I denotes the type of the consumer that the firm is dealing with. Similarly, the firm's expected revenue is the expected value of the endowment that it receives from consumers, and so this will also depend on the consumer's type. So with probability PI, the firm is receiving an amount EB, and with probability 1 minus PI, the firm is receiving an amount EG. So the expected value of the endowment, depending on type I, is PI times EB plus 1 minus PI times EG. Now let's go on paper and study the firm's costs and revenues in more detail, and will provide a graphical way of representing the firm's costs using what are known as isocosts. Okay, so now let's consider how to represent the firm's costs and state contingent consumptions contracts in general graphically. So I've prepared a diagram here with on the horizontal axis consumption in the good state. So if we remember that a contract, a typical contract denoted C, has two dimensions, an amount CG and an amount CB. So this, if I accept contract C, then my consumption in the good state will be CG, and my consumption in the bad state will be CB. So using these two, because it's a two-dimensional object, we can represent it as a point in the plane. So if we remember, for example, the endowment was also a two-dimensional object, some amount EG and some amount EB, where EG was assumed to be greater than EB. Okay, so how do we draw this? Well, let's have an amount EG there, and I know that EG is greater than EB, which means we're going to be below the 45-degree line. So let's pick a point, say here, and label this as E. So if I read on this axis all the way across, I will get EB. Okay. So this is how we represent contracts. So a contract C could be some point over here. Any point in this space represents some contract, each point being described by two dimensions, an amount of consumption in the good state and an amount of consumption in the bad state. So let's analyze the firm's costs a bit more, and then we will represent those graphically as well. Okay, so if we remember the firm's expected cost, it's going to depend on the type. So type I, let's make a note over here that I is equal to H, L, or X, high risk, low risk, or unknown type. And the firm's revenue is the expected value of the endowment. That's the thing they're going to take off the consumer, which would be PI, the probability type I is in the bad state, multiplied by the value in the bad state, EB, plus 1 minus PI, multiplied by EG. Okay, so that's the firm's expected revenue. It depends on the type, but once the type is known, it's a fixed amount. Okay, and then in general, the cost of a contract, again, will depend on the type. It's evaluated in exactly the same way as the expected value of the endowment. We just take the expected value of the contract C in the same way. Now, to represent the costs of different contracts, we're going to use what are called ISO costs. And I believe you've heard this term before, ISO costs, ISO meaning single costs. So it's going to be a straight line in this case. It's going to be a line in our diagram, in our state contingent consumption space or contract space. And every contract along that line is going to have the same cost. So what can we say about these? Well, one way of writing the condition for an ISO cost, if I use a differential notation, if I say that the change, D being a change, the change in expected cost along an ISO cost is equal to 0. Okay, so that would be one property of an ISO cost, of a single ISO cost. Cost is not changing. So if I break this cost down, it's either changing because CB is changing or because CG is changing. So I could rewrite this condition as PI, which is just a constant, multiplied by the change in CB, which is our y-axis, plus 1 minus PI, multiplied by the change in CG, which is our x-axis, along an ISO cost. This equals 0. Okay, now with some rearranging, of course, I'm really using the implicit function theorem here, but this is a simple way of kind of remembering it. So dy over dx, the slope of an ISO cost, dCB over dCG, that's our dy over dx, will be minus 1 minus pi divided by pi. Okay, so this is a single number. This is sometimes called the odds ratio. Okay, so they have constant slope. so they're straight lines, but that slope depends on whether we're talking about high risk, low risk, or the unknown type. Okay, now you can show mathematically that because we assumed that pH is larger than PL, that we must have 1 minus pH over PL over pH. If we compare that to 1 minus PL over PL, that this is greater than this, okay? Which means essentially that this is more negative than this, and so the ISO costs when I'm dealing with low risk types are steeper than the ISO costs when I'm dealing with high risk types. Okay, now it's quite difficult to kind of first of all get from here to here. It's not difficult, but it's easy to go wrong. And also interpreting this condition as, well, this one is steeper because it's more negative can go wrong. So here's a simple way of remembering it. Essentially, if we go back on the diagram, if I look at the different contracts with the same cost as E, okay? Now, what does that mean? Anything that costs the same as E, well, the expected value of E is my revenue, so anything with the same expected value we could think of as a zero profit line, okay? Now, if I look along the 45-degree line, the equation for that is CB equals CG. Okay, there's no uncertainty here. Consumption is the same in both states. Okay, so if I think about this endowment E and say, well, where along this line would there be a risk-free equivalent if I'm dealing with a low-risk person? Let's just draw that point in here. Okay. Now, if I'm dealing with a high-risk person, I know that their endowment must be worth less. They're more likely to be in the bad state. So essentially, I just come down and say, well, if I'm dealing with a high-risk person, then it has to be below this. Okay, so that's a kind of simpler way of remembering that if I now draw a straight line through here, and a straight line through here, we can see that this zero profit line I'm going to associate with low risk types has a higher expected value than this line, which I'm going to label as the zero profit line for high risk types. Okay, so if I'm dealing with a high risk consumer, any contract along this line, anywhere, if I'm giving them that contract and taking the endowment in return, then I'm earning zero profit. Anywhere along this straight line, the line labeled pi L equals 0, any point along this line has the property that the expected value of those contracts is the same as the endowment dealing with a low-risk person. So these are the zero profit contracts when I'm dealing with low-risk people. These are going to play a very important role later because in equilibrium, we do expect the firms to earn zero expected profits. So the equilibrium contracts are indeed going to be on these lines. But let's just use these a little more just so we can understand. If I pick a point, let's say contract C1 here, well, what can I say about this? If I look at the low risk ISO cost through that point, it's quite steep. Okay. I can see that C1 is on a higher ISO cost, so it's further away from the origin than the zero profit line. Okay, so along this line, selling to low risk people, I'm definitely earning negative profit. Okay, now if I pick a point in the middle here, let's call it C2, then, well, if I sell C2 to low risk people, I could draw an ISO cost through that as the same slope. Remember, the slope of this is minus 1 minus PL over PL. That's the slope of a low risk type ISO cost. And if I'm looking at C2, well, C2 is on a lower ISO cost than the endowment. So the endowment has a higher expected value than the contract C2 when I sell it to low risk types. And so my profit would be positive. Okay. So for instance, a monopolist would want to get onto the lowest. If they had no other concerns about competition, they would want to be on the lowest ISO cost possible in order to get that endowment E. Okay. Now, of course, this point C2 makes profit for selling to low risk types. But if I look with high risk types, if I just draw a line through that, my diagram doesn't become too cluttered. You could see that it's on a higher ISO cost. C2 is on a higher ISO cost than the zero profit line if I'm selling to high risk types. And so selling contract C2 to high risk types, I would expect to lose money. Okay, I would have negative expected profit. Now that we know how to represent the firm's costs, both mathematically and graphically, it's time to study the other side of the market, consumers. So what will we assume about consumers? Well, we're going to make a very basic assumption that they are risk-averse, expected utility maximizers. Now, to keep things simple, as promised, we're going to assume that all consumers have the same von Neumann-Morgenstern utility function, little u. So we're assuming that all consumers are equally risk averse. Of course, this could be changed, but we're keeping it simple just to clarify our point about changing information assumptions only and keeping everything else the same. So we're going to assume that the von Neumann-Morgenstern utility function u is a strictly increasing function, so it has a strictly positive first derivative wherever you calculate this derivative, and also that this function is strictly concave to capture risk-averse preferences. So if we calculate the second derivative of this utility function at any point, then we will find a negative number. Now, when looking at a contract C, this two-dimensional object with some chance of receiving consumption level CG and some chance of receiving consumption level CB, we can calculate the expected utility of this contract. And of course, it's going to depend on the type of consumer. So if we consider a consumer of type I, the generic type, which could equal H, L, or X, then expected utility is going to be with probability P subscript I. The consumer receives consumption CB, which gives them utility. So we multiply PI by the utility of CB. And then we add to this the probability of the good state for this type of consumer, 1 minus PI, multiplied by the utility of the level of consumption CG that the consumer receives in the good state. Let's now go on paper and study consumer preferences with a very familiar graphical tool that we've seen before, indifference curves. Okay, so now let's talk about consumer preferences and representing those preferences graphically. So remember that if a consumer accepts, or a consumer of type I accepts a contract C, then their expected utility will denote E subscript I U of C is equal to the probability that depends on their type. So the probability that type I finds himself in the bad state multiplied by the utility of consumption in the bad state plus 1 minus PI, the probability of the good state, multiplied by the utility of consumption in the good state. Okay, so this is the expected utility of a contract C in general. So if we want to represent this graphically, we'll be familiar with the concept from the microeconomics that you've seen before. We're going to use something called indifference curves. So lots of different contracts. The consumer will prefer some to the other, and so on. But if we look at an indifference curve, it's a curve that connects all contracts in our contract space for which the consumer is indifferent. Okay, so again, we could use the implicit function theorem here to calculate the slope of an indifference curve, but let's use this idea of a total differential, which is essentially the same idea, perhaps a little more instructive. So a property of an indifference curve would be that the change in expected utility along that indifference curve would equal 0. Okay, so that's a basic property of an indifference curve. Utility is not changing, or expected utility is not changing in this case. And if we think about how utility can change, well, this would give us some constant Pi, and then if we're changing the bad state consumption, that's going to change utility. And by how much? Well, if we take the marginal utility at that point and then multiply it by the change in consumption in the bad state. Let me write this out and then I will explain a little more clearly what's happening. Okay, so this would be the total differential. Essentially, there is some change in the good state consumption, okay, as we're going from one contract to another. This change is changing the utility. How so? Well, that's what we call marginal utility, and that's being multiplied by how likely that change is that change is to occur, i.e., the probability of that particular state. Okay, and so all of this is just expanding this change in expected utility into its respective parts. This has to add up to 0 along an indifference curve. We can use this property that along an indifference curve, expected utility does not change, and so this total differential will equal 0. We can use this to find the slope of an indifference curve at any given point. So by rearranging this equation, we find that the slope, the derivative of CB with respect to CG, remember CB is the y-axis and CG is the x-axis, and then I've put this vertical line here, which just is a way of annotating our derivative. So this derivative, and then we add this note saying, by the way, change in expected utility when we calculate this derivative is equal to 0. Well, this is equal to minus, and then we have this odds ratio term that we're familiar with from the slope of isocosts, and then an additional term, which is a ratio of marginal utilities. Here, the marginal utility of consumption in the good state divided by the marginal utility of the bad state level of consumption. You can use this equation to prove that that high-risk types will have flatter indifference curves than low-risk types. Remember that both types have indifference curves that are downward sloping, and so both have negatively sloped indifference curves. But the low-risk types have indifference curves that are more negatively sloped. Again, you can use this expression to show this, but if we go back on paper, there's a good intuition for why high-risk types have flatter indifference curves and low-risk types have steeper indifference curves. So let's do that now. So I've prepared a contract space diagram here. Let's pop in some point, which is our endowment. EG is greater than EB, so it's below the 45-degree line. Now, I could just examine this expression and say, well, if I know that pH is larger than PL, okay, then I can calculate an expression that compares this slope for a high-risk type with the slope for a low-risk type, okay? And then remember that the more negative the more negative this slope is, the steeper that indifference curve is. Okay, well, let's just use our intuition to make this a little easier, because it's good to develop the formal techniques and good intuition to make sure we're not going wrong. So if we think about these individuals, if I'm a low risk type, let's just put some point here, okay? And we'll say that this point is what we call the certainty equivalent for a low risk type of their endowment. So it's an amount of money with certainty that makes the consumer willing to swap their endowment. Okay, just willing. Okay, so that's what we mean by, you've seen certainty equivalence before. Now, the zero profit line here would be, because they're risk averse, okay, we know that they would accept less than the zero profit line. So let me just draw one zero profit line here. Pi L equals 0. Okay. Now, I know that this low risk consumer, obviously he would love this point, but he would be willing to accept something less. Okay, so the difference between these two is sometimes called the risk premium. If I'm risk averse, then this is strictly better than E. This fair amount with certainty is strictly better than the risky amount with the same expected value. And so I'd be indifferent between something smaller and E. So my indifference curves are going to look something like this. They're going to curve underneath. Okay, so there is an indifference curve for a low risk type. They have that convex shape. Okay, this is one of these strange things to remember, that the utility function is strictly concave. Indifference curves, because of the concave utility function, you end up with strictly convex indifference curves. Okay, so that's, and you can see why this risk aversion pulls the indifference curve underneath the kind of zero profit line. Now, suppose we're talking about a high risk person. Well, a high risk person knows that their endowment is less valuable than a high risk person knows their endowment is less valuable than the low risk person's, and so presumably they would be happy to accept something less. Okay, so if I'm just looking at this 45-degree line, perhaps that point there is the certainty equivalent for a high risk type, and so his indifference curves are flatter than let's label that IH, are flatter than the low risk type's indifference curves.